if you vote. Yes. You'll talk about my son. Then just one last shot. So what I did. Or where you check. So you do really don't know what we do. People will do this.
Okay, 7:30, and we are going to get started. So I want to thank Jonathan Kistner for our opening slide, a beautiful picture of Mars he took recently with a 16-inch homemade telescope Uranus C camera. So thank you, Jonathan, for submitting that. Okay, here's our agenda for this evening. And before we get started, we'd like to see if there's anyone, if this is your first time you've been here, we'd like for you to raise your hand, tell us your name, how you found out about the JSC AS, and what your interest is in astronomy. Okay, so hold on. So you're saying it was on there in the past, but it wasn't there this month? That's very interesting, because we've had a lot of people say they find us on Meetup, but I have no idea how we got on there. Somebody must have been paying for us then. Oh, okay. I don't know. Okay, well, I'm glad you're here. Who's your two friends? Oh, the other ones. Don't go there. Oh, that's pretty good. Yeah, Europa, right. Okay, who's your two friends? Oh, you have my apologies. Sympathy. Great. Great. Well, welcome. That's right. That's all there is to it. Anybody else? First time here? Is this your first time here? Who are you? She's our main speaker. So, okay. Okay, I'll introduce you in just a minute. All right. Anyone else? First time here? Everybody else looks familiar. Very good. All righty. Very good. Now, we have two email distributions. If you want to be sure to get the emails, send your emails to David at the bottom, starhopper757@gmail.com. In the past, we've had a meetings only, but they may not happen any longer. So if you want to get all the emails, send your thing to David. And Stan is holding up a clipboard right now. If you don't want to write that down, there's some tear offs up there. You can tear one of those off has David's email address on it. You can send him an email, say, I'd like to get on the email distribution. All righty. Reminder to presenters. So when you guys get up here, please use the podium pointer, the mouse pointer, this little doodad here. It's in the mouse pad so that people online can see what you're pointing at. And our stream mic is in the laptop and the auditorium mic is here. So you can't really move around too much, guys, because if you go over here, nobody can hear you on the stream. So you got to kind of stay in this general area. Okay. So our main speaker tonight is Dr. Mane. And I'm going to tell you a little bit about her before she comes up here. She is so anxious, isn't she? Okay, Dr. Mane is a staff scientist at the Lunar Planetary Institute. Her research focuses on the study of chemical, microstructural, and isotopic characteristics of meteorites. She analyzes calcium aluminum rich inclusions, or CIAs, to decipher chronology of early solar system events, observes the recorded nucleosynthetic anomalies in them, and studies their microstructural characteristics to determine the mechanisms of CAI formation. She also analyzes Martian meteorites for their hydrogen isotopic composition to understand the evolution of Martian water reservoirs. She is working to build her career as a scientist in meteoritics and planetary science. You guys ever heard the word meteoritics? Anybody ever heard that? You've heard it. Okay, one guy heard that. That was a new one. I had to look that up to see how to pronounce it. That's a good one. Oh, did he say that?
Yeah.
Yeah. It's meteoritics. Great. So we all learned a new word here tonight. All right. One of Dr. Mane's highest aspirations is to work on pioneering methods which significantly advance knowledge about the building blocks of the solar system. She has a strong interest in developing laboratory techniques to study cosmochemistry and isotope geochemistry of meteorites and sample returns from various planetary missions. In addition to her research, she actively participates in outreach activities for the Lunar and Planetary Institute, which is probably why she's here tonight. All right, join me in welcoming Dr. Mane.
All right. So I'm Prajakta Mane, and
Just hit return.
Oh, okay. Perfect. So today I'm going to be talking about some of the earliest rocks in our solar system and what do they tell us about the planet formation. So, perfect. So meteorites and meteorite impacts are actually a very common phenomena in our solar system. So here is an example of the meteor crater from Arizona. This is about this is a meteorite impact crater that's close to Flagstaff near Arizona, and is one of the famous craters that formed because of an impact of a meteorite. Earth has lots of these meteorite craters, but we've also observed various comets and asteroids being impacted in other planets as well. So here is an example of the comet Shoemaker-Levy that impacted on Jupiter, and it was a very spectacular event. So these kind of very turbulent activities are very common in our early solar system. So I'm going to share a little bit of a personal story about one such encounter with a meteorite. I was doing my PhD at Arizona State University in 2016, when on 2nd June 2016, there was an event of a fireball. Here are the trails that this meteor left in the sky. And here is a Google map that basically shows probability of finding these rocks in this area. So Arizona State University is in Tempe. It's about 82 miles in that direction. And this is middle of nowhere. This is the White Mountain Apache reservation. And there is no civilization there, like nobody lives there. So I had the opportunity with some other folks from ASU to go hunt for this meteorite. Here is our team. That's Dr. Lawrence Garvey, who is the curator of meteorites at ASU, and a bunch of us grad students. And these three gentlemen here are meteorite hunters. So that's a actual real full-time job. You can actually be a meteorite hunter and collect these rocks here. So it was super exciting. And this is what the terrain looked like. Lots of vegetation, lots of terrestrial rocks, and I promise you there are meteorites here. So do you want to make a guess or try and identify a meteorite in this picture? You can just point and I'll... Over here?
Yes.
Okay, that's one guess. That's actually okay. Any other guesses? Over here? Ah, okay, because it's dark, it's black in color. Okay. Any other guesses? Over here? Okay. Over there? Okay. All right. So so the actual meteorite is right here. It's really tiny, but can you see the difference compared to the rest of the rocks that are there? It looks black and gray. It doesn't show that rusty weathering color that you see in these rocks. In fact, there are two more meteorites here in this picture. Let's see. So it's actually a small little fragment. It is a small little fragment that like impacted and formed a really tiny crater right here. And then it broke apart in 3 pieces and then landed over there. So most of the meteorites that we find are actually very tiny. You would expect them to be really large, but as they get bigger, the probability of them we finding them gets also smaller. So most of the meteorites that we have are actually quite small. So in our 4 days of expedition with 6 of us, we found about 16 meteorites in these 4 days. And here are all of the meteorites that we collected. So the largest one was probably like a strawberry, size of a strawberry, and lots of small ones as well. So one of the really fascinating things about meteorites is they are usually named after the location where they are found. So if you ever want to have a meteorite named after you, all you have to do is buy a large land and then wait for a rock to fall there, and then you can name it after yourself. So this was Arizona's fourth meteorite fall. And this was named as Sibiku or Dishibico, which is the native name for this location. In this picture, you can see that the outer crust or the outer layer of this rock is very dark in color. This is something called as fusion crust. So when a rock like this comes into the atmosphere with a lot of velocity, there is a lot of like heating and charring of the outer layer. This is probably like less than a millimeter, very thin veneer that you have over here. And that's called the fusion crust. This is one of the most important identifying criteria for meteorites. And as you can see, there are pieces where things broke off, and the interior of this meteorite is pretty light in color. It's actually very fresh, not much weathering, not much like iron oxides that you see in the terrestrial rocks. So fusion crust is one of the ways you can identify meteorites. Most of the meteorites that we have in our collection form very early in our solar system. Here is an artist's depiction of what the early solar system looked like. You have a protosun at the center, and this is surrounded by a disk that is made of gas and dust, which is kind of rotating around the sun. This is way before Earth or any large terrestrial planets have been formed yet. So a lot of these meteoritic components formed at this time. They came together as sedimentary rocks, like, they stuck together, and they survived for 4.5 billion years for us to like study them, analyze them in the lab. So it's really cool. And it allows you to understand some of the earliest processes in our solar system. So there are different types of meteorites. And I have two here, for example, I'll pass them along. The meteorites that form and do not undergo any sort of further heating or differentiation, they're almost like sedimentary rocks of the early solar system. They're called chondritic meteorites. They're chondritic stony meteorites. Some of these meteorites, the parent bodies, grow large enough that they undergo melting because of the radioactive heat and also the gravitational heat. And because of this heating and melting, all the heavy material like iron and nickel sinks to the core, and the outer material, the outer mantle, is made of silicate material, like very common terrestrial rock called basalt. So these are called the differentiated meteorites. Some of these meteorites, after the disruption and breaking apart, we have the cores of these meteorites. They are iron meteorites, and here I have an example of an iron meteorite. Some of them that are forming at the mantle, which are made of silicate, are called achondritic stony meteorites. So this is chondritic, meaning it's very primitive. It has not undergone any melting. And then achondritic, that means it has undergone melting and differentiation, but still it's stony in composition. And then somewhere between the boundary of this metal-rich component and the silicate-rich component, you will probably have a mixture of both. So here are these really cool, really amazing, pretty-looking meteorites called pallasites, where you can see large silicate crystals, which are primarily olivine, that is surrounded by some of the metal, which is found in the core. So I'm going to pass them along. Yes, you have a question.
Why didn't you call the palisade meteorite?
That's a good suggestion. I'm not quite sure how they were classified, but the types that you see, type C, type M, they are the analogous asteroids that you see, and you compare the spectra of these asteroids with the samples that we have in our hand. And I don't think we have an analog for palisade yet. So if we find it, we'll maybe name it type P. Yes.
So I'm wondering.
Uh-huh.
Finding the magnet meteorite. And I find a whole bunch of them.
Mm-hmm.
How do I actually determine whether it's really a meteorite?
That's a very good question. So there are certain criteria. One of the really interesting one is the fusion crust. Like the dark material, the veneer that I showed, that is very exclusive of meteorites. You have something called as desert varnish that happens on some of the terrestrial rocks, and sometimes people confuse that with fusion crust. But if you have a fusion crust, that's a very good criteria. A lot of meteorites are rich in metal, but not all of them. And some of the very primitive one, the chondritic meteorites, have these things called chondrules, which are these spherical objects, and I'll have a better picture of this later. If you find them, that's another criteria to find out, to figure out that it's a meteorite. The best way to identify that it's a meteorite is basically bring them to the lab and analyze them. That would be the final way of knowing for sure. Mm-hmm. Any more questions? Uh-huh. Yeah, they are chondritic stonies. That's a very good observation. So this meteorite is a ordinary chondrite. It is chondritic. However, it has undergone a huge amount of thermal metamorphism. So we didn't see any chondrules in there. That's why it looks more like a chondritic meteorite. But it's like it's almost, I think, classified as type 7. So type 1 is no metamorphism at all. And then it's progressive grade up to 7. And 7 is the highest grade of primitive meteorites that you see that have undergone metamorphism. So it's highly metamorphosed, and that's why you don't see any chondrules in it. It hasn't seen actual melting, but it is significantly metamorphosed. All right. So most of the meteorites that we have in our collection, they come from the asteroidal belt between Mars and Jupiter. However, and there are thousands and thousands of these meteorites. So here are examples of different asteroids that you have here that could be parent bodies of a lot of these meteorites. About 250 meteorites come from the moon. They have been identified as lunar meteorites. And we also have about similar number, 250, maybe a little bit more now, that come from Mars. So we have some Martian meteorites. We don't have samples from Mars yet. We are waiting for Mars sample return. So this is our only way of actually analyzing samples from this planet, which is super cool. Other than meteorites, now these are poor man's space probe, but we have also analyzed, brought back samples by various missions. So some of the very popular ones are, of course, the moon rocks, the Apollo samples, and also the lunar missions that brought back samples from the moon. We also have a comet sample return mission, which happened in about 2005, the Stardust mission that brought some material back from a coma of a comet called Will-2. We also have samples of the solar wind that were collected by the Genesis mission. We have interplanetary dust particles. These are few micron-sized particles that are collected in the upper stratosphere by high-altitude planes, and a lot of them come from comets, and we know this by analyzing them in the lab. We also have micrometeorites, and now we have two of these new missions called OSIRIS-REx and Hayabusa-2 and Hayabusa-1 that went to some primitive asteroids to collect materials and brought them back. Yes. Any what? We haven't identified them yet, so no. There were some suspects, but we haven't found them yet. All right, so meteorites are really, really important, and they tell you a lot about our early solar system, how it formed, and all that. So I just picked 4 or 5 significant discoveries that changed our understanding about how the solar system formed, and I put them together here in the presentation. These are the analysis of meteorites is called cosmochemistry, and these are the greatest hits of cosmochemistry. So how old is the Earth? Unfortunately, it's a very dynamic planet, right? So there is a lot of recycling and a lot of activity happening on the Earth. There is plate tectonics. So how do you date materials from the Earth? It's really hard. But meteorites, some of the meteor crater that I showed you earlier had this iron meteorite called Canyon Diablo. A lot of these meteorites probably differentiated at the same time when our Earth formed. And by dating these meteorites, we can also interpret the age of the Earth. This work was done in 1956. Maybe some of you have seen the Cosmos episode about using lead dating to know the age of the Earth. It's a very fascinating study. And this was determined by Claire Patterson in 1956. The age of the Earth was 4.55. This has been a very significant discovery. All I do as a cosmochemist or someone who dates these kind of rocks is just add more and more decimal points here. And make it more precise. But the initial estimate or the determination of age of the Earth is very solid in 1956. And this is how, because of these meteorites, we know the age of the Earth. How old is the solar system? So this is an example of one of the chondritic meteorite. This is one of the famous meteorite called Ayande. And this meteorite fell in 1969. Just right before the Apollo samples were supposed to come back to the Earth. And this is like lots of material fell. And our labs were ready for the analysis of these extraterrestrial material. So this is probably one of the most well-studied meteorite that we have in our collection. This is a carbonaceous chondrite. It's rich in carbon, but it also has these objects that are called chondrules. These are basically molten droplets of silicate material, iron and magnesium, that were floating around in the space and then solidified and were accreted onto this meteorite. That's where chondrites get their name from. Other than chondrules, one of my favorite objects in these meteorites are called CAIs, or calcium aluminum rich inclusions. They are refractory, they're highly refractory, meaning they form at very high temperatures compared to chondrules. And we think that they are the first form solids in our solar system. So how do we know that they are first form solids? So, well, they have been dated by various radiometric dating techniques like lead, which is a direct absolute chronometer. But we also have other relative chronometers like 26 aluminum, 53 manganese, and all of these converge to this number of 4,567.3 million years. That's the oldest CAI that has been dated. And this is the 0.0 or the reference point for our formation of our solar system. Sometimes it's really difficult to understand millions of years or comprehend what that timeline looks like. So let's translate that into a human lifetime. Let's just imagine that you have a person who has lost their birth certificate and also lost their memory. It's like dating or knowing the time of birth of this person with the uncertainty of 18.4 hours. So we know, you can't do that for actual living human beings, unfortunately. It's like 2 or 3 years based on your dental records. So we know the age of our solar system way more precisely than what we can say about a living human being. thanks to these meteorites and the analytical techniques that are available to us. So this is another significant discovery. The next discovery is that we are all made of star stuff. Carl Sagan said that, but we actually have evidence for that. So a lot of these meteorites have been studied for their isotopic composition. One of the earliest understanding, like the earliest clue that came that some of this material is not forming in our solar system, but coming from some other stellar systems, is this neon isotopic anomalies. So what they did is took this meteorite and heated step by step and analyzed the isotopic composition of the gas that was released out of it. So you see this gray bar, that's where most of the terrestrial stuff forms. So somewhere around 1000 degrees C, you have this huge anomaly in isotopic composition that cannot really be explained by any physical or chemical process. Like nothing can fractionate isotopes that with that drastic change. So this was, we don't really know what the carrier phase for this component is, but this was like a clue that some of the material came from other stars and not really actually formed in our solar system. This was named as phase Q, and this was our first evidence. However, after that, we've actually identified something called as pre-solar grains or stardust. So here are examples, or these are the TM images of these pre-solar grains. This is the stardust that's made of silicon carbide, and the other grain is graphite. And if you look at the error bars, the scale bars, this is about 1 micron, and that's about 1 micron. So they are maybe less than 5 microns in size. And trust me, these are some of the biggest pre-solar grains that we have. An average size of a pre-solar grain is about 150 to 200 nanometers. So they are very tiny, very small, but these are actual physical objects that formed in some other stellar environments, and they were brought to our solar system, and they were preserved for those many years. So how do we know that these materials are actually pre-solar? So isotopes is actually a very important, they provide very important clues to identify these materials. Here I have an oxygen isotopic plot. So oxygen has 3 stable isotopes, 16, 17, and 18. Isotope geochemists like to measure everything in ratios because measuring absolute has huge error bars. But if you're measuring something relative to each other, the error bars kind of shrink, and it's easier to make these kind of measurements. So on y-axis, you have 17 to 16 ratio. On x-axis, you have 18 to 16 oxygen ratio. Everything that's within our solar system, on our Earth or moon rocks or say Martian rocks, they all fall at the intersection of these 2 dotted lines over here. And look at the scale over here. It's logarithmic. It's not a linear scale. That means the changes are pretty drastic. And a lot of these, like, few micron size grains or even few hundred nanometer size grains show huge anomalies and isotopic compositions that cannot be really predicted or created by any physical or chemical process in our solar system. A lot of the models, stellar nucleosynthetic models, have predicted different isotopic compositions. So that's how we know that some of them probably come from supernovae, others come from AGB kind of stars, some of them are maybe nova grains, etc. And these predictions kind of match these analysis from the lab. And that's how we know that these are pre-solar grains. So this is another really cool discovery that a lot of this material that we have in meteorites, even though really, really tiny, is forming in other solar systems or other stellar environments. The next really exciting discovery is actually from a terrestrial rock. This is the evidence of supernovae material that are exploding in our surroundings, and we actually find a physical evidence of this. So this is an artist's depiction of a supernova that has multiple shells as they're expanding and exploding. And maybe this is how it probably looks like. But if you look at some of the terrestrial samples, these are very special samples. They're called ferromagnesian nodules that are deposits that grow very slow, just like our tree rings. They grow and they have these growth rings that you can see in this picture. You find these materials at the bottom of the ocean. So when you collect them and you actually analyze each layer, you find some of the really weird isotopic composition. So iron-60, for example, is a short-lived radionuclide that can only be synthesized in a supernova setting. There is no other way that you can produce this. It's extinct because all the iron-60 that formed at the beginning of the solar system has been decayed to 60 nickel, which is this daughter product. But these ferromagnesian nodules actually show evidence of live iron-60. And if you date these ferromagnetic nodules, you see a spike at about 2 million years from time zero, like 2 million years going back in time from today, and also maybe at around 7 million years. So this is an example of a live radionuclide that formed in some sort of a supernovae and then came to Earth, came to our solar system, came to our Earth, and then was deposited in our ocean sediments that you can actually analyze. So this was another very cool discovery that tells you about how different elements in the early solar system form. So how do planets form? We do study these samples, which are pretty tiny in the lab, but these days we also have some really spectacular telescopes that can allow you to observe a lot of planet formation in other solar system, like live. Currently, that's happening. So here is an example of the Atacama Large Meter Array, which is in Chile. And this telescope has been really, really successful in imaging lots of different disks, protoplanetary disks. So this is probably how our solar system looked like 4.5 billion years ago, as all these different planets were forming. And as you can see, there is a star at the center, and then there is the disk of gas and dust that is revolving around it. Sometimes you see various gaps. People have interpreted them to be planets that are probably forming. If you take into consideration all the meteoritic material that we find in our solar system, that shows a very distinct dichotomy in their isotopic composition. And this was observed like pretty recently, 2011, and we don't really know how this dichotomy is formed. One of the hypotheses to explain this dichotomy is actually looking at these protoplanetary disks. This is planet formation currently like ongoing right now. And the isotopic evidence that you see in the meteorites is about from 4.5 billion years ago. So this dichotomy has been explained by early formation of Jupiter. Just like in these disks, you see all these planets that are forming and clearing out the gap. That similar phenomena happened very early in our solar system that separated the two reservoirs that have different isotopic signatures and probably had this isotopic dichotomy that we see in these meteoritic materials. So what you see from these rocks 4.5 billion years ago can actually tell you how planets form in current extrasolar systems that we can directly observe with our telescopes. So that's a very cool connection between cosmochemistry and astrophysics here. Another really fundamental and exciting discovery was finding these CAIs in some of the cometary components that were returned by Stardust mission. So CAIs, as I said, are the oldest samples, oldest materials that formed in our solar system. They are also refractory. That means that they form at very high temperatures, and we think that they form very close to the sun. However, comets form about 35 AU or maybe beyond, so very far away from the sun. However, a lot of these materials were actually observed in the Stardust sample that was written by the Stardust mission from comet called Will-2. A lot of these materials were CAIs and chondrules that form very close to the sun. What that suggests is early solar system was a very turbulent environment. So here is your proto-sun, and there was a lot of mixing and turbulence going on, and material that formed very close to the sun was thrown away tens of AUs and was like accreted into this comet forming region, which is actually a pretty exciting phenomena that we probably wouldn't have figured out if we didn't have these samples to analyze. So very recently, we analyzed some of these samples that were returned by Hayabusa 2 mission. It's a JAXA mission, the Japanese Space Agency, that returned these very primitive materials and from an asteroid called Ryugu. And a lot of these materials show, we did this analysis was done at the Johnson Space Center led by Ann Ewan. She's my collaborator there. And what we found here is that a lot of these materials that probably formed close to the, the solar to the sun, but they also show materials that are very rich in these pre-solar materials and isotopically anomalous organic materials that are very abundant in comet forming region. So these clasts are probably coming into the asteroid forming region from far beyond from the comet forming region. So there is a lot of mixing that's going on in the early solar system. So these were some of the highlights. My research actually addresses some of the fundamental questions about the solar system formation. How did it form and how did it evolve? Some of the phenomena or the processes that I study with these materials is what sort of processes actually formed a lot of these rocky materials. Condensation, aggregation, lots of melting and evaporation, and planetary differentiation. At the same time, where did these materials form? Like close to the sun, very far away from the sun. A lot of isotopic signatures and chemical signatures provide evidence for where the location of these materials. And at the same time, when did all these processes form? Like what were the time scales of these processes is another important question. So one of the tools that I study for my own research is short-lived radionuclides. And here is an example. There are various short-lived radionuclides that have been used to date early solar system materials. My favorite is 26 aluminum. So aluminum has only one stable isotope, that's 27 aluminum. 26 aluminum is a short-lived radionuclide that decays to 26 magnesium, and it has a half-life of about 0.7 million years. So all the 26 aluminum that was created at the beginning of the solar system has now been decayed. And all you can find is the excesses or the isotopic anomalies in the stable isotopic composition of magnesium. So how does this chronometer work? Now let's take into consideration an object. So for example, if you have a rock that has different minerals, these different minerals are going to fractionate. So here on the x-axis, I have 27 aluminum, which is the stable isotope of aluminum, and 24 magnesium. So like we like to study everything with ratios. So this is basically the proxy for how much aluminum was accommodated in these different components. And on the y-axis, we have a ratio of 26 magnesium, which is the daughter product of the decay of 26 aluminum, and the stable isotope of 24 magnesium. So as the rock forms at time 0, you have different minerals that come out of it. Like, if it's an igneous rock, you're going to have different minerals crystallizing, like olivine, spinel, etc. All of them going to have different chemical composition and fractionate along the x-axis here. Once they fractionate and solidify, the radioactive clock starts ticking. So after a while, is going to increase the composition, the ratio of 26 magnesium, because aluminum decays to 26 magnesium, in the proportion of how much original aluminum was there in this rock. So because of 26 aluminum, you're going to have this slope. This is called an isochron. You have another object that's forming maybe a little bit later after the first object formed, and now it is resetting and having the fractionation along your x-axis. At some point when all of the 26 aluminum has been decayed, you're going to have this correlation or the isochron that is basically frozen in time. And for the second object, it's going to be a little bit less amount of 26 aluminum that is decaying. So it's going to have a slightly shallower slope. So when I say that this is a relative time chronometer and not an absolute chronometer, what we do is basically take the slopes of these different rocks and then calculate the time difference of the formation of these two different events, and it gives you a delta t and not actually an absolute time difference. The advantage of this chronometer, however, is that it gives a very high the temporal resolution. Some of these materials have been dated with a really, really high precision of like few thousand years. So how do you actually analyze these isotopic compositions? So there are two methods. One of them is primarily an in situ method. So this is an instrument called SIMS or NanoSIMS, secondary ion mass spectrometer. This one is at NASA Johnson Space Center. Here what we do is take a polished slab of a meteorite and then bombard it with an ion beam. Usually the diameter of this ion beam is like few hundred nanometers to about a couple of microns in size. So really, really tiny. It gives you an in situ like analysis and isotopic composition of that material. This is an in situ technique. It gives you a spatial context of actually what it is that you're analyzing in the lab. The second way of doing this is actually taking the rock and then completely dissolving it with harsh acids and then separating out magnesium and then analyzing it on another mass spectrometer called MCICPMS, multi-collector inductively coupled plasma mass spectrometer. That's here what you see. This gives you a very high precision and isotopic analysis of these isotopes. However, you do lose out on the spatial context of these what these ages actually mean. So these techniques are actually complementary to each other. So one of the questions that I addressed with my research is, when did these chondrites and the chondritic components form? Here is a thin section of a meteorite that is a false color X-ray map. So magnesium is shown in red, calcium is in green, and aluminum is in blue. So a lot of these things that show bluish green composition are the calcium aluminum rich inclusions. That is something that I analyze using this chronometer. So here is an example of how a calcium aluminum rich inclusion looks like, with a backscattered image here, backscattered electron image, and then this is an X-ray map that again shows magnesium in red, aluminum in blue, and calcium in green. So this is actually called a compact style calcium aluminum rich inclusion, or a CAI. We also have something called as fluffy CAIs. So these are basically dust bunnies that came together and did not really undergo any sort of melting, whereas the compact ones have undergone lots of melting. So these are, even though they're tiny, like a millimeter size, few millimeter in size, they've seen some sort of melting, and that's why you have this spherical structure. These CIs have been dated by various chronometers. Here is your 26 aluminum that gives the most precise age, relative age. But you also have other things like manganese chromium, and then you have lead age that also tells you the absolute age of formation for these meteorites and their components. So by analyzing this, you can, a lot of these CIs have these really interesting features around them. So this is a backscattered electron image of a portion of a CAI. This is a CAI interior. What you see is that you have these tiny layers of different minerals that form around them. So I don't know how much, if there are any geologists in the audience here, but this has been described as an early solar system stratigraphy. Just like rock layers that you find that, that are sedimentary, they deposit on top of each other. You find something similar in the very early solar system as well. Just the scale difference here. So these are pretty macro size rocks, but over here, what you see is a few micron size layers that you see. So part of my PhD thesis was actually dating these different layers to see what are the timescales of formation of the CAI with respect to these rims that you find around them. So just analyzing CAIs and finding isochrons, we actually know that most of these CAIs formed really early and in a very short time period. So these isochrons are very precise. They define a canonical ratio for 26 aluminum, which is about 5 into 10 raised to negative 5. And they also define a very precise, very tight isochron here. Based on these analysis, we know that the precursors of these CIs formed very early. So here I have Caltech plot where there is nothing on the y-axis, but on x-axis you have time after CI formation. So do you remember that CI that was 4,567.13 million years? That defines the time zero. And everything is after that. So this is like very ancient time of our solar system that goes up to maybe first 6 million years. So here are your CI precursors. Because of the precision of the 26 aluminum chronometer, we can determine that most of these precursors form really quickly, like few thousand years, maybe 6,000 years to about 20,000 years. So that's very, very precise and very quick. Now, analyzing these rims around these CAIs, so I selected 4 of them for my analysis. And here are the 2 isochrons for the first 2 CAIs. So the interior is shown in the green colors here, and the blue are the rim isochrons here. And the time difference, if you calculate between them, is about 2.2 to 3 million years. Now imagine this material, which is like millimeter to centimeter size, pretty tiny object that basically floated around in the early solar system for 2 to 3 million years, and after which the rims around it formed. That's pretty significant, and that has a lot of astrophysical implications. But those were just the first 2 CIs. The other 2 CIs actually show that some of these rims form contemporaneously with the CI, with the actual interior of the CI. So the largest time difference could be about 440,000 years. So what does this tell you about the early solar system and the chronometry of different things? So this is the CAI formation. This is probably the melting of the CI. Everything happens within first million year. And then you have the rims. Some of them form almost contemporaneously, and others take about 2 to 3 million years after the CI formation. At the same time, we have chondrules. They have also been dated by various chronometers. A lot of the chondrule precursors also form very early, a little bit later than the CI precursors, maybe about age difference of about 1 million years. But a lot of the chondrule melting goes on up to first 4 million years. Other events in our solar system, we also have differentiated meteorites, like those iron meteorites or the meteorites that come from the mantle of a differentiated parent body. All of them show differentiation also happens very early in the solar system, say starting from like first million year to up to first 3 million years. So a lot of these events are happening simultaneously in the early solar system. Also, based on the meteoritic evidence, we can also put some constraints about when Mars forms and when the Jupiter forms. So 50% of Mars, based on Martian meteorite analysis, we think 50% of the material that accreted onto Mars happened very early within the first 2 million years of the solar system. Similarly, Jupiter accreted about 30 Earth cores of its equivalent of Earth masses into its core within the first million year, and 80% of the core of Jupiter accreted within the first 4 million years. So you're forming all these centimeter to millimeter size objects. At the same time, you're also forming these giant planets. Some of these meteorites or asteroids show evidence for aqueous alteration, a lot of activity for fluid that is also being dated. Some of them formed really early, others are up to like 6 million years. So what does this plot tell you? You have CAs and chondrules that are very primitive materials that formed that are hosted in these chondritic meteorites. They're centimeter to millimeter size objects that form very early, maybe up to 5 million years. At the same time, you have planetary formation and differentiation. You have objects, planets like Mars and Jupiter also forming very early. And then in some parent bodies, you have activity of water that is also being dated. So planet formation is not really like a linear process where you have a disk that has made of like gas and dust that slowly starts cooling, and then you have condensation and these different minerals coming like forming that come together as these dust bunnies, and then slowly they grow together to form bigger materials like centimeter to millimeter size objects, forming like meter size objects and then maybe kilometer size objects. So it's not a linear process like that. All these processes were happening in the early solar system simultaneously, probably different parts of the disk. And that's what this meteoritical record tells us, that all these processes, the time resolution for these processes that we see based on these meteorites is really, really high. And it tells you that planet formation is not a linear process, it's probably very turbulent, and lots of things happening simultaneously at different parts of the solar system. So I see that it's about 45 minutes. I do have some other slides, but I would like to stop here and see if there are any questions.
Yes. I understand you showed several.
Mm-hmm.
Do you attribute strategies totally fine?
That's a really important thing. As a cosmochemist, when I'm dating these layers, one of the most important question is what phenomena you're dating. What is the process that has formed these? So, and that's a very complicated question. I don't think I have a straightforward answer for that. Let's see. I think when so here is the first plot, the first motivation for my research that I showed. And this how is basically what are the different processes that could form these layers. It could just be like, condensation where you have a hot gas that is very slowly cooling and forming these layers around these CAIs. It could also be like nebular processes, like part of the CI melts, evaporates, and the residue left behind has these materials. Or it could be things that are condensing out of these, like melting out of these. So various processes, and I think we see evidence for all of them in these rims. Some of them show presence for like direct condensation, some of them show evaporation and melting. So a lot of these things are happening simultaneously. That's why it's really important to analyze isotopes and also analyze the textural context for what you're actually analyzing. So that basically tells you not only the age, but what age is that indicating, like what process you're dating. Yes.
Yeah, so there's been a few papers that looking at short-lived radioisotopes.
Mhm.
126.
Mhm.
All of it, early formation of the solar system.
Right.
And they're basically having a fairly unique contribution because it basically controls the amount of volatile you have. And moves a lot, right?
Mhm.
So that ultimately controls the.
Yeah.
So have you seen, is that kind of good research? I mean, that seems very important for like exoplanet research.
Absolutely. Absolutely. That's a very ongoing hot research topic. And I didn't really talk much about it, but a lot of the terrestrial planets like Earth and Mars, did they accrete with all these volatiles? And like, did they already have the water? Or did they accrete dry because of the heating of 26 aluminum? We lost whatever water they had. And then later delivery of other asteroids and comets from the outer solar system brought this water to Earth. That's a very fundamental question because if we understand that, as you said, for other exoplanetary systems, we have some understanding about how they would form their volatiles and would probably allow you to address if there is a possibility of habitability or life on these other exoplanets. Well, I think Earth probably formed with very little water. And one of the ways to determine where the origin of this water came from is again isotopes. The hydrogen has two isotopes, well, three isotopes, but we can actually measure two, the hydrogen and deuterium. So the D to H ratio is one of the very key things that people analyze. I have done that research on some of the Martian meteorites, but I didn't get to speak about that here. And a bunch of different like chondritic meteorites and even cometary samples, analyzing them, and then it kind of gives you a tracer as to what could be the source of water on these terrestrial planets. So that's a very hot ongoing research for sure. Mhm. Yes. Um, so that's a very good question. I think in order to understand that, the volatile question is a little bit different than the age dating that I showed here. The DH ratio is one of the key ways of telling, like, suggesting what are the sources of water. And for Earth and also for Mars, we think it's very much similar to what you would find in a lot of primitive asteroids like chondritic materials, probably comets as well. However, there is a complication associated with it. Hydrogen diffuses very quickly. So even if you have these meteorites and even if you collect them very fresh, sometimes contamination is a major, major challenge. The second challenge is it only has two isotopes. So there are certain physical processes that can fractionate it, and then other is the actual using, like, using it as a tracer. And just because it has only two isotopes, it's really difficult to differentiate it, separate out these two processes. So maybe like finding some other kind of volatile element that has more than two isotopes could help, but right now we don't really have something like that. So it's a complicated ongoing research. Hopefully more samples like, OSIRIS-REx or Ryugu. These are very fresh samples. They have not been contaminated by any terrestrial processes. And that can tell you a lot about what is the original composition of these materials. Yes.
So with the disk, so all the moons in our solar system form disk, they were just captured by the planets, or each one?
Each one, I think, probably has a different story. Yeah, we only have samples from our own moon. Mars has Phobos and Deimos, and there is a JAXA mission, and we have a lot of participation from NASA, like lots of American participating scientists on that mission. Hopefully, it brings back samples in 2029, I think, and that will tell a lot about how both these moons formed. It could be a different process. They're significantly smaller than our Earth, our terrestrial like moon. So there is that. For giant planets, of course, we don't have samples, but then there are lots of dynamic studies that suggest that some of them are probably captured objects, some of them are probably like the original moon moons that formed with the planet. So I think it really depends on which planet and which moon you're talking about. Yes.
Might the surface of the moon be a good place to? Would there be any benefit to analyzing the moon?
Absolutely. So we do have samples from the moon. I don't know if we have actually identified meteorites on the moon. We have identified them on Mars, though. I think there was, which I forget which rover, but that identified a very foreign rock, which was identified as a meteorite. We have not found any Earth rock on the moon, as far as I know, or any other, like, foreign rock on the moon yet. I think it needs to be explored a little bit more.
Be any easier? for moon?
Ah, that's a very good question. I think one of the biggest challenge for analyzing anything is, let's see. Do I have a picture of the labs that we analyze? A lot of these instruments that we have, they are massive and they're very heavy. So it would be really difficult to put them on a spacecraft and then send them on the moon. So this is the nanosims at NASA Johnson Space Center. And here is my collaborator, Anne, and she's basically fixing this part. So, and it has a huge magnet, which is quite heavy too, which allows you to measure a lot of these isotopic compositions with a lot of precision. So I think it would be very expensive to put something like this on a spacecraft and analyze it. So bringing samples back is probably the best way we can analyze these materials. Yes.
The mass specs.
Uh-huh. That's true. It has an orbit wrap. So yes, the technology is always evolving, and I think it has been successful in analyzing isotopic compositions of certain elements like hydrogen and oxygen. I'm not quite sure about this. I probably need to go back and read a little bit more about it. But a lot of the analysis for these materials that we do is requires pre-processing in the lab too, like, crushing them, dissolving them, and all that. So, of course, as mass spectrometers get better and better, they'll give better precision on other planets, but there are certain things that we can do here on Earth that are not yet very replaceable for these analysis. Any more questions? Yes. Mm-hmm.
Is it the area?
So that's a very ongoing hot topic that people keep debating. There are two competing hypotheses for that. The first one is like what you mentioned, that probably some comets and asteroids impacted on the early Earth and brought lots of like water and other volatiles. The other one is that early in its formation, Earth had a magma ocean and surrounded by the gas in the disk. And there is some possibility that some of this hydrogen was dissolved into this magma ocean that created, that retained some of the water. Competing hypothesis, hydrogen is the only isotopic signature that basically can tell you which one is true and which one is not. So I think we need the right samples to do a lot of this analysis. And there is still lots of unanswered questions for this topic. All right. Okay. Thank you.
Alrighty. No. I have to go through it to not kill the stream.
Here.
No, don't.
It's 75 cents.
That's okay. I don't, it'll kill the stream if we do anything else. Okay. All right. So, Rick, need you to pay attention for a minute. See Dan up there? Dan
up there.
Dan, right behind you. Dan brought some Sky and Telescope magazines to add to your project. They're right there. Dan's right behind you. All you gotta do is turn around and look at him. There he is. Yeah. Okay. So you. Okay. So did you bring other ones? Tell us. Okay. So great. So they're up there for anyone who wants some free Sky and Telescopes, and you guys can talk to each other about. And Dan brought some tonight. Okay. Very good. Thank you for doing that. Okay, after the meeting, we'll have the meeting after the meeting at Mod Pizza, the one that's in front of HEB up at Clear Lake City Boulevard in El Dorado. Everyone's welcome to come. You guys can talk about meteorites and all that kind of stuff. All righty. Oh, and for our break slide, we have a picture from Stan, picture of the moon he took with his William Optics 132 refractor and an ASI 294 MC Pro camera. So thank you for contributing our break slide, Stan, which I don't know why I'm not seeing Stan right now. I know. Oh, there he is. Sorry, Stan. You usually sit over there. Okay, so we will take a 10-minute break and then we will pick up with the second half of our meeting. 10 minutes. See you then. Is your stuff? What's your stuff?
I was there when I got here.
Oh, really? That's weird. Wonder who left those.
Hey, can you show me my flag real quick? I didn't even have a chance since I sent it to you to look at it. No, I could not. No, I guess. Sure. You see the what? Oh, I believe it. Get a big telescope and enjoy it. Cool. So Trevor, it's about 1 minute, right? Thank you.
I just muted it for the minute.
What?
I just muted it for the 10-minute time for you. Okay. Somebody made a comment that they weren't hearing the question. I mean, this microphone over. We're not carrying the microphone. Hang on.
Thank you. Okay, it's time to start.
Okay, our 10 minutes is up and we're going to get started. Okay, the break's over. We're going to get started.
Okay. All right,
The break is over and we are going to get started. Brandon wins the prize this time. Oh no, Dan's going to win the prize. Dan, we're trying to get started. Come on, guys. Come on, we got to start. Okay. Okay, I got 2 members' minutes. First one, Visual Mysteries of the Universe. I want to make you guys aware. I don't know if any of you know Larry Mitchell, but he's actually, you know him? He's actually a local astronomer, and he's come out with a series of books, and I've got a set of them. They're really good. Visual Mysteries of the Universe, and they're available on Shop at Sky. They're based on the advanced observing programs they have at the Texas Star Party. So if you've ever been to the Texas Star Party, each year they have these advanced observing programs. And Larry has taken these things over the years and years and years and put them into these books. What? Yeah, and these books are good. They're available on Shop at Sky. There's 3 of them right now. They're divided by right ascension, so they go through the year by right ascension. He's going to come out with another one. There's a 4th one coming out to finish up the year, but these 3 are available now. I just want to make you guys aware that these things exist. They're pretty new. And they're really high quality. So I got a set of them, and they're really good. And you'll also see some pictures from the Holland Observatory in these books. So, all right, Green Bank Observatory paint. Where is he? He's not paying attention. John, this is for you. So please pay attention. There are many people who went into this presentation just for you. Yeah. So at the last meeting, that guy there that wasn't paying any attention to me says he wants to know how does the sunlight and heat affect the dish antenna and its observations. Remember, John? You probably don't even remember asking that. Yes. Oh my gosh. What are we doing standing here talking about this? You don't even know what you asked. You're asking how does the heat on the dish affect the observations? You don't remember that? Okay, just forget it. We'll just skip this thing. Okay, so last meeting, I kind of said, well, it has something to do with the painting and the coating and material, and it decreases the sunlight. And that's what I kind of thought it was, which I was lucky that was true. But okay, so many people, Laura Lazorek from the Green Bank Telescope, who's actually a granddaughter, that fellow right there, Jerry, is his granddaughter, and an employee of Green Bank Telescope, and Rick Slater right over here, who has been studying radio astronomy in the great courses, have combined their knowledge to answer your question. And here it is. Okay, so here's the issue. If visible light and infrared was focused into the instruments, they would damage the instruments of the telescope. It'd be like a gigantic magnifying glass and make a mess out of everything, right? It'd also heat up the structure, which cause deformations, which would be bad loss of sensitivity because you're not a parabola any longer. And if it behaves as a classical black body radiator, it can influence the observations. So they paint these things, and as I showed you the Green Bank Telescope a minute ago, the 100-meter telescope, they paint it blindingly white light in the light, black and white in the light spectrum, and infrared in the black is black. Okay, infrared is black, so it radiates heat very effectively. And it'd be a problem to basically destroy the receivers if you didn't have these properties. It also scatters the visible and infrared light in all directions, so it does not go into the horn. It actually scatters in all directions, and it may or may not contain tiny glass beads within this white paint that they paint it with. There was some mention of that. Okay, the paint being an excellent radiator keeps the dish cool, and it does not heat up in the daytime. Otherwise, it would cause the dish to warp. So what is this paint? The paint is high reflectance, flat white, number 6 from Triangle Paint Company. That's what they're painting this thing with. Protects the dish from heat accumulation, high infrared diffusion, which is scatters the infrared, so it does not focus it into the horn. Reduces the surface temperature, does not distort or obstruct the transmission of receiving signals. The paint's white and invisible. Again, it decreases the heat absorption from the sunshine, and black in the far infrared, making a good radiative cooler. Black, like a black body radiator, right? Here's a graph. They sent us a nice paper about this paint on the Green Bank telescope. And here's a plot of its performance. So along the x-axis, you have a blank piece of aluminum, right, minus air. That's a piece of aluminum sitting out in the sun, minus air. And along the x-axis, the y-axis is the skin of the telescope that's been painted with this paint minus the air. And so what you see is these dots around here. You see as the temperature goes up, the piece of aluminum gets hot. Gets hot right along with the sun heating up. But in the y-axis, it does not go up at the same rate, right? So this white paint is keeping the actual skin of the telescope from heating up as a normal just piece of aluminum would. John, aren't you glad you're getting so much attention?
Yes,
I guess so. All right. Anyway, so that's that. So how about other dish antennas, like a radio telescope that an amateur may use like us? Okay, so if you look at one of these dish, like a Dish 500 dish, like I showed you the project last month about measuring the temperature of the moon, they're painted with this kind of rough gray stuff. So they themselves actually diffuse the light and IR also. And what I did is I took this dish out and I put it in the direct sunlight, focused it on the sun, and the horn on it doesn't get hot at all. It does not focus that heat into the horn at all. Now, the horn stays nice and cool, no issues. And so that's evidence that the heat is not being focused into the receiving antenna. And there is heat on the dish. The dish itself actually does get hot, but it radiates unfocused in all directions. It's just a hot thing. It's not focused heat. It's actually just radiates in all directions, just as any hot surface would. And at the bottom here, this is the sun plot I did for you, John, just for you. This is a sun crossing where I pointed this thing at the sun, and you can actually see we get a nice signal from the sun. And so it's not just all a whole bunch of heat. It's actually getting at 12.7 gigahertz. Actually can do it just fine. It's actually pointed directly at the sun. So it is effective to be used. The sun does not melt, but, oh, my butt's on the next one. All right, so you may be wondering, what is the actual spectrum of the sun? So here's the sun right here. So on the higher frequencies or shorter wavelength, the sun actually operate like as a black body irradiator, and you can use Wien's law to figure out what the peak, the wavelength is at the peak of this curve here. So if you use Wien's law, you can actually calculate. If you know what the temperature of the sun is, which is 5780 Kelvin, you can find out that the peak of the wavelength here is around 502 nanometers. But in the radio wavelengths, you come down here, and it doesn't follow this black body curve any longer. You can see with a disturbed sun, the thing actually comes way out here. Now, if this had been still a black body radiator, this would correlate to a sun that was like 12 billion or billion Kelvin. So if you looked at it in the radio and you thought, well, this thing's a black body radiator, no way. See, you'd have the sun is way too hot. But these emissions down here are not from black body radiation. They're from all the magnetic fields and other things that are going on within the sun. Now, so what would happen if we did not have this kind of paint or this kind of surface for our parabolas? Just yesterday, this guy on Facebook posted this. This is on the Radio Amateur Facebook posting. This guy posted this thing, and he has a dish which actually does reflect the sun and infrared, and it melted his horn. his receiving antenna. So he made a mistake. He has this thing in a radome, but he foolishly took it outside from the radome and he pointed the thing at the sun and it melted his receiving antenna. So if you did have a dish like that, it would work like a gigantic magnifying glass and it would ruin everything. So that shows you basically how good, even on these satellite TV antennas and things, how good their properties are in not doing that. Yes.
So that's why if you look at their dishes, right, they have the offset horn, and that's directly to not have the heat go right into the horn.
That's not it.
No, I'm talking about the one.
That's not it either. That's not it. All that offset is they're an offset parabola. It's actually a section of a parabola, and then they set the dish off. It's still focusing all of it into the horn, but it's not focusing the infrared and the light into the horn.
They designed it that way just in order not to have all radiation go into the horn.
That's not it. It's the white paint and the surface that keeps it from doing that. It's all it is all. This guy, no, this guy has a shiny surface. His dish is not painted. That's the point. Yeah. Okay. So this guy has an unpainted or his surface is reflective, so that's why it melted. But in the case of the Dish 500 and the Green Bank telescope, they are. Yes. Force. I have no idea. All I know is this guy posted this thing and he said he melted his receiver because he took it out of the radome and pointed at the sun. Accidentally. He pointed at the sun accidentally, but I pointed mine at the sun on purpose for the purpose of this talk. I pointed straight at the sun and did the sun crossing, and I can testify that the horn stays nice and cool. I mean, it's just plenty cool. It's not focusing the heat into the horn at all. But this guy, because he has a different surface, the coatings on his surface is completely different. It actually did reflect the IR and the light. Yes.
Point out the offset on the Green Bank, the big Green Bank telescope they've got. It's the reason they did it was that they get all the information from the disk. And it's the same thing that you have with yours,
Right.
that you have.
It's
offset everything that the disk can give you.
That's right. It's a section of a parabola is what it is. And that, if you imagine, here's a parabola, they just took out a section of it and then they offset the horn. So you're actually getting that section of the parabola, but there's no, if you look at like on a Newtonian telescope, you put down these spiders, you get diffraction from that. It's the same thing with a radio telescope. On my other radio telescope that has, well, I'm sorry, if you have the vanes just like you do, you actually get diffraction, but they're trying to get away from having diffraction from the vanes. Do you agree with that, Rick? Okay. Anybody else? All right, we're moving on. Anyway, so John, don't ask any more questions. And if you do ask any questions, remember what they are. Okay, Rick's going to bring us historical eclipses. Rick Slater.
Since I got here. So, all right. So what am I doing here? Yeah. All right. Oh, enter. Let's see what we got here. Let me get the other glasses.
That one.
Yeah, the one that says enter. Okay. All right. That works out well. Okay. Actually, I tried to make just a kind of a fun historical thing of some historical eclipses here in the U.S. And I actually stumbled on one picture, which was from, I believe, 1878. And I just stumbled on the picture. I grabbed it, and then I went and Googled and found out a little bit of information about it. The other one came out of one of these old sky and telescopes on the 1925 eclipse. And so I thought I thought the pictures are kind of fun, and it actually had some information on what they were trying to do and everything. So I thought I'd just throw it together. And of course I had to negotiate extra minutes
with our president here. So, and it took a while to do that, but we got it. We got there. So anyway, all right, enter. Okay, the 1878 solar eclipse. And this picture was taken in Fort Worth, Texas. And what was kind of interesting about it was that scientists, including those outside Texas, came to observe the eclipse and capture data. And what was interesting was, I mean, there were a lot of places they could come, but they came to Texas. Thomas Edison was there, they said, with a device to measure solar radiation. I don't have a clue if he's in this because he would have been fairly young at the time. And scientists were hoping to discover a new planet called Vulcan, which scientists thought lied between the sun and Mercury. So that's what they were planning on doing. Enter. Okay. The last picture was black and white. They colorized it. And I got to tell you, when you colorize these pictures, they look a whole lot better. Anyway, there were newspaper accounts described the darkness, and and the newspapers were all over this one. They smoke glass to view the eclipse safely. I'm pretty sure that didn't work out real well for them. And of course, the eclipse was what it usually is, about 2 minutes, almost 3 minutes. Let's see. They said that they made a big deal in the article about how it was considered a watershed event for science, for studying the sun especially. And that's all the information I was able to find on this. 1925, there was an article, and the article was really pretty good, but there were some really fun things, I thought, on how they approached this whole thing. I did put up there, they stuck in there, eclipse 4 seconds late, but what a brilliant show. I guess anything to sell newspapers. It's about 110 miles wide. They said it was the largest star party in history, hundreds of thousands viewed, because it really eclipsed that whole New York City and greater area into Connecticut and down into New Jersey. The next eclipse in New York is in 154 years, or 2079. Reported to be the first color photograph of an eclipse. The photographer exposed 15 plates for 4 of the total eclipse, and pretty much it was done with colored filters. This is the thing that really was interesting to me. The Navy actually had a dirigible that was designed for high altitude, as a high altitude observatory. It was about at 8,000 feet. The Navy's chief photographer just about froze to death out there that day, and they weren't over the city. They were out, I think, I don't remember if I put it in here, but 19 miles off of Long Island. And what was probably fairly interesting about this whole thing was that it was the first observatory from a dirigible ever done. And the Navy actually had it. And there were several other ones that came about, smaller ones, but this was a fairly large one. There were 25 Army Air Force planes that also recorded motion and still imagery of the event, flying at 120 miles an hour. And I've got to think that it was fairly cold at 125 miles an hour. Here we go. Again, it was the Vulcan hunt, except that this one, I guess they decided not to stop looking for it, because apparently 10 years earlier, Einstein's theory of relativity had apparently put that to rest, that it wasn't because there was a planet in between Mercury and the sun. One machine, as airplanes were called, was equipped with a radio transmitter, flew at 10,000 feet. The transmitter generator quit just after they got off the ground. And so the first ever broadcast never ended up happening. And you've got here, they call it the Vulcan hunt, the photographers. One of the things about it was, and I don't remember the exact number, it's in there somewhere. I believe there were 10 actual observatories that were covered under this solar eclipse. Funny thing, the police feared pickpockets, which was a real big deal in the late 1800s and early 1900s, really up until the 30s, probably 40s. And they were afraid that pickpockets, when it got dark, were going to be going at it, but it was only, just a little less than 3 minutes. So nothing actually happened there. They sent out thousands and thousands of these pamphlets to everyone because they wanted everybody to know about the eclipse. Let's see if we get more. And I've got to tell you, the pictures weren't the best, but they were, the best I could get off the magazine article. There's one of the pictures that an amateur actually shot of the solar eclipse. And there you can also see the coverage in the other photograph. It swept from Minnesota to New England, and many noticed Jupiter, Mercury in the darkened sky. One, because everyone brought their kids out. In fact, they brought their babies out in the carriages, but they were talking about some of the comments that the kids made, because the kids were there freezing to death. And one of the comments was, "Hey, how come we can't have one of these in the summer? Why does it have to be in the winter?" So, and it was January, so it was just freezing. For the eclipse photograph, typical films had a narrow dynamic range. They had some shades of gray. They really didn't have a lot, and that's why when you look at the old black and white movies from the 20s, it's just not all that good because the film just wasn't it didn't have enough shades of gray. That's probably the easiest way to put it. Now, what they could do, but in this case, there was absolutely no real reason for it. What they would do is just change the developer. And in fact, in my bachelor's, that's what we did for forensic photography. And that is, we would actually adjust the different chemicals in the developing agent to bring out as much dynamic range as you wanted. But this was actually the one picture that made the newspaper, and it was by an amateur. It wasn't one of the professionals. Let's see. Yeah, President Calvin Coolidge and his wife came out for it. And if you notice, if you look carefully, you can see he's got at least glass plates. Hopefully they were good glass plates. This was actually a kind of an interesting picture. A trick shot, as they put it, done at Cornell. And the photographer took 18 exposures of the same film, 17 brief ones showing the thing, and one longer one to record the corona. And this, too, made a lot of the magazines and the newspapers. That's it. I think I made my 5 minutes, didn't I? Next, we got Al with, is that right? Oh, you got more slides. Oh, those were the backup slides. Oh, okay. Those are in case there are any questions. Okay, Al, what's up in the sky? Plus, what's going on in astronomy today? -5 minutes.
I'm very excited this talk. I got a chance to go out to a star party at TSP a couple of weeks ago. So I got a chance to actually look at some of the objects that I've been talking about. So first meteor showers. There were supposed to be some meteors showers lingering from April, and I didn't see very many. I usually see quite a bit of meteors just on an average time out. I did not see very much. And then this month in May, it's already sort of started. It's the, I don't know how to pronounce that, Aquarids, Aquarius. So the emanating center should be around Aquarius, and the peak had already come by on the 5th or 6th of May and goes through the 28th. I don't know much about that meteor shower. So we'll start off with binocular objects. I picked the Crab Nebula. This month I was going to pick basically Libra and Scorpus as the kind of center, if you will, of where some of the objects are I wanted to look at. And that's a little bit low on the zodiac, but this is the time of the year that, other than Sagittarius, we get in the low southern sky. This time of the year, we get Scorpus and Libra and a couple other constellations. So it's really cool to look in that area of the sky, really low on the horizon. So I've never looked at the Crab Nebula, Crab Globular Cluster with binoculars, so I don't know how this shows up. And this is a magnitude 10 galaxy, M98. And if you do this with like a telescope, it's really cool because you got this little NGC 4186 here, and you kind of gauge the seeing quality of your telescope because the M98 is very easy to find, which is the same as 4192. Sorry about that. But then you can come down here and see if you can see this 4186. And you can kind of check how good your telescope's working or your eyes or the quality of the night. So that's a double slide. So one of the big objects to look at this time of the year, especially at TSP, we have people come from all over the country to come down to southern latitudes. You can see this from Florida. Florida has a host of other problems like wet skies and a lot of moisture in the air, or sometimes a lot of wind. And so a lot of people come down from other parts of the country to see this amazing globular cluster called Omega Centaurus. And I dug up some interesting information that I didn't know about. I think a lot of people know that globular clusters circulate around the spiral arms of our constellation, or of our galaxy. And so many of them have come through and back and through the arms. And one of these satellite, the Gaia, I think it's called Gaia satellite, takes pictures of, I think it takes pictures of a lot of galaxies. And I don't know how to pronounce this either. Fimbule tool stream. I'm sure that's a person's name. I just hacked it. But you see these colored dots here, this tricolor dots, like rainbow there. Those are stars that they have seen moving that are within our galaxy, but they're moving all together. So the theory is that Omega Centaurus came through the galactic plane and then had some of these stars stripped away from it and have been dragged behind it, so to speak. And they've tracked the movement of the stars, and that's what they infer. Very interesting. But I thought that was really cool about an object we look at a lot. Next object. Oh, this is so cool to look at in the telescope. I don't remember seeing it those many times before, but the Hamburger Galaxy Centaurus A, it was really cool. A suggestion of somebody else to go look at. It is in a neat line from Omega Centaurus is really low. And then there's a line that goes up vertical, and this is the next object up from that. And what I dug up is some information about this. And with all these great telescopes, you know, Webb and our ALMA micro radio telescope array, they can see these jets coming out from probably a black hole that's in the center. of this galaxy. But in a telescope, like a visual telescope, probably photography as well, you see this really black line through here, and it's just so cool because it looks like a sort of a round globular cluster type of thing, but it has that stripe through it. It is so cool. It was one of our funnest objects we looked at every night. The next one is, this is what I call the object of the trip. This is the Bug Nebula. It's a cool little planetary nebula. And when we were looking at this, we didn't get anything like that right image. But the left image, it looked more like a galaxy with a hook on the end. And I don't know why that is. Several times I went back and looked in sort of like all the galaxies around to see if it wasn't another galaxy. But nevertheless, I was doing 674 magnification to look at this, pretty large in the scope. It was very cool. And then another really neat object is the eyes. The strangest thing is the picture on the right is obviously a really cool, high quality picture. The picture on the left is more like what you see. And these two galaxies are flipped around and are the two little galaxies. Let's see if I can spot these right here, kind of turned upside down. And but when we were looking at this, we weren't really looking at these two galaxies. I think they were a little bit fainter. But when I got everything centered, we were looking at this cool triangular formation. And this is I can never pronounce that name, either the Marchand chain or whatever. These stars are all part of that. But when we got these three photos together, it was such a cool triangle, and it had like a group of galaxies in the center. And so it was quite a sight to see. It was sometimes when you see something for the first time, it's very exciting. And then this is another one that I'd never really looked at before, and this is called the box. And I just really love seeing multiple galaxies in one shot in the eyepiece, and especially when you get different ones. I couldn't see this wispy nature of this one right over here, but you could see the nice edge-on galaxies, very cool. And then you have this real fainter one over here, which is really great to identify how the night's doing and so forth and so on, as I said before, I like to kind of do. And so I always try to include a few ARPs. You know, these are very faint objects. These get into magnitude 15 or so. But I did look at this. This is one of my cool faint objects I looked at. And I like it because you get almost like three types of galaxies: an elliptical, a pretty large spiral, and then a small galaxy that's really tough to see. One more ARP, and that should do it. And this is ARP 94, and I really like these because the picture on the left is kind of what I saw, and I really love it when you got two of them kind of smashing together. The picture on the right, actually, even though it's very pretty, doesn't look quite as awesome as that picture on the left, at least visually. If it looked like that on the right, it'd be very pretty, but the collision is what I was going for. Okay, so now we're going to get on to, I didn't put a slide in here for what's happening in astronomy. So I put these kind of in reverse order, but I was really enamored with this one, and I'll show you why. I can't even pronounce it, Circunus West. So this constellation we don't ever see. You would have to be like below, as the Tropic of Cancer is the highest one. The Tropic of Cancer, you'd have to be closer to the center of the planet, because this is fairly low in horizon. I think you have to be like at 25 degrees or 20 degrees or something like that. But they did some interesting studies in this, and these are two areas of the sky where you see these. Let me start off with what the slide says. So several things I thought were really cool. They have this dark energy camera, 570 megapixel. It's a pretty big array. It's not the hugest one. I have one larger later, but they're looking at all these little galaxies that are disturbed by new energy coming off of new protostars. You know, so much research is on the beginnings of time and what happens in our early formation of planets and everything else. And it's really cool. The next one is a video showing how if you zoom in from this outer picture, I'm just going to hit that and see if it runs. So watch how it zooms in. We're going in further. We're going in further. We're still going in. I'm glad it's running because I was so fearful it was going to hiccup. We're still going in. And this is like the final picture where they go into. I'm going to say this is that you should go on their website. It's called the NOIR, NOIR lab.com. If you can find that orange picture, there is not just a video and some other pictures, but there is a picture where you can zoom in. Remember, 570 megapixels. You can't see that fully on a monitor that's only HD. So they have a way that you can zoom in like on the screen. So you can literally take this picture like right here and then zoom in even further and see those other little pictures I showed you. And you can see them in the actual shot. You know what I mean? They didn't have to process that extra just to get those two previous pictures. I don't know how to go back, but it is so cool when you have such a huge camera. I don't know. This is the Galaxy Sir Cunis. Excuse me.
The website.
Oh, Noirlab, NOIRLAB, and this is one of the newer camera systems. And there's just so much information. So I guess this was done with the Department of Energy, this big camera. But let's go on to the next one, or we'll take all day or all night. So this is a little bit less exciting. They've been trying to understand more about dark matter, and I don't understand exactly how you infer dark matter from this, but they used a Subaru telescope and they zoomed in this one portion of the Perseus cluster core, and they could see this bridge of material. So then I can get the feeling like something hit another object, but I don't get the dark matter bridge. But I think if you look at the cluster and then imagine zooming in so far and deep like this, they're really looking deep into what's going on in the interaction of this cluster. Okay, one more, no, two more. So this is one of the first pictures that they finished. Once again, the big telescopes, they want to go really far back in time as far as they can. And this is using James Webb. And this is one area of the sky. And one of the things they're trying to figure out is not just what kind of galaxies were there right after the Big Bang, but like there's other effects we've understood about the universe, which is the galaxy clusters and the spindly nature of the universe. It's not evenly distributed. It's not like some kind of a bomb and everything goes in all directions. It's all filamentary. And so they wanted to study more and more about that. So they're not just looking at the really furthest away objects, but they're looking at all the periods in time from one to another to see the relationship of how it like evolves. And I don't think this picture represents it. I found a better picture later. So once again, if you go online, you can find more information about all of this stuff. Yeah, so we do know that the early formation was, we can see at the very earliest galaxies are not usually spirals. They're more elliptical or that type, or more of a glob. And they can tell that there's a lot more star formation going on. And they actually go as far as to say a lot of the galaxies we see now are kind of in a status quo, kind of a dormant stage, that they're not really growing and they're not really forming a lot of stars. I don't know. So this is one of the coolest. This is my last one. So one of the very coolest projects is this spacecraft called Lucy, and how do you go backward, Doug? What? Okay, so this is a picture of the asteroid, the latest one that I just saw. It shot up. They launched the satellite in 2021, and it's going to go to like 2037. But this shows you the purple line is the track that the satellite's doing in order to hit essentially like there's like 9 asteroids it's going to go across. But it's very cool. You can go online and go and see more about this. And remember, the website that I use is called physphys.org, and then the category is astronomy, and you can go and research this stuff all more and more. Thank you.
Promise to be quick. All right. Past events, I think people are going to be talking about TSP, and I think Mark's going to be talking about the trip to the X-Bar Ranch. That's cool. I have heard, as many have, a lot of back chatter about TSP, and people weren't exactly pleased with it. Apparently, the attendance was way off, and the price was very high, and you had to pay for the full week, even if you went for a partial week, as I understand. So, I don't know. Okay, coming up on June 8th, Hack Winery, September, we got Okie Text. Some more events will filter in as we go. Trying to work an arrangement with Challenger Park. We've got, I think, one of the libraries out there is still talking to me, and we're supposed to be getting a series of at least 2 or 3 more events going on with the Armand Bayou. So we'll see how that all plays out. So October 16th, that's still the tentative for the club's trip to Fort McCavett. That'll probably be a sure thing. El Dorado, November 1st is going to be the Sun and Moon Night at the George. I forgot and neglected to put Aaron is going to revive A-Day, but he's going to be running it at Insperity. Insperity is just within, it's up there in Humble ISD. It's a really cool observatory. You owe it to yourself to take a look at the equipment and things that he's got there. He runs a good show. And then we actually close out the year right now with November 15th at the Magnolia Creek Golf Course. I was able to pull it all together. I want to thank the people on this slide for the outreach they contributed in 2024. I do have pins for you. Deep appreciation and thanks for the 11 events that we had in 2024. Our hours and time were logged with the Night Sky Network, so it kind of got us back into that. So if I haven't given you a pin yet, please get me one. Now, the next slide, I don't want to make this a competition, but the folks in red are the ones who really helped carry the weight for this year. So definitely Chris Randall, Bob and Leslie Eaton, Mark Pacellas, Reed Klotzer, and Stan Lamb. I very much deeply appreciate your efforts. If I missed anybody, you have my sincere apologies, but I tended not to do so much the 4th. These were all the events that we did here. So if I haven't given you a pin yet, come find me because I've got them in the back. And there you go. 15 billion miles on it, and the radio still works. Interstellar salvage.
All right, Mark's going to tell us about the X-Bar Ranch trip. Come on, Mark.
I stand between you and pizza. All right. Let's see. The trip was scheduled for last month, April 24th to actually April 28th. But we all left on the 27th because of the forecast of weather. So we all took off on that Sunday on the 27th. So we all pretty much bolted one day early. Total of 5 people went. Brandon, Alan and his wife, Karen, Mark, myself, and my wife, Hilda. Al is on there. I had an asterisk next to his name, but I guess Dougie changed it to TSP or something. The asterisk was because he was our coordinator for the event. Problem is he missed the exit off of I-10 and he drove another 230 miles and he showed up at the Texas Star Party. So he blew us off for a bigger crowd. That's all right. This was my first time at X-Bar. I was really impressed with the facility. The room to the bottom right is the main room where you go to meet. And it's where the kitchen is. The kitchen is on the left side. Awesome facility. They really cater to us. First time there. I was impressed, and I'll definitely go back, even though we had some issue with the weather. That's why my background has some water droplets on it. That was our setup. There was 3 of us. We had a Dobbs. I had my Smith Cassegrain, and Alan's rig is in the background. It is in the far right side where he had a camera set up. I think it's a Dobbs, right? Is that yours? Okay. Yeah, so that's what we had, and that was facing away from the buildings. We were on the back side where the cabins are. Both Alan and myself, we brought our campers. They have RVs, spots there with Wi-Fi. So it's a really good setup. That's my wife Hilda, which her name is spelled Hilda, David. So this was a shakedown from my camper. It was the first time taking it out of Houston area. And again, really great location, great accommodations. Look at that blue sky. You would have thought we would have had a good night that night. That was our second night. First night, to give you a rundown, first night, the 24th, it was clear from 10 to 12, very high humidity, condensation everywhere. By midnight, I gave up. I don't think Brandon even tried that day because it was just so hazy. 25th was probably our best day. We went from the clouds cleared at about 10 to 1 in the morning. 26th, we were hoping, all the forecasts were saying we were going to get good weather. And that's why on the bottom, I was talking about the 3 apps we were using, and all of them were in disagreement. Some of them said we had clear skies when it was solid overcast. So none of them really impressed me. I don't know if you all had any good luck with TSP, with the apps, with what they were saying at the time. So hopefully you had better luck than us. But 26, we did have some clearing, but then the lightning to the north and to the west made us think that it could possibly rain. And by then we all knew we were leaving the next day. So we all started packing it up and we left. Some pictures that I was able to take. I have a C Star. It's the S50. That wasn't in the pictures for our setup, but if you're unfamiliar with it, it's the size of a shoebox basically, and it's for. I was testing new features of it, so that's basically what I was able to get. You know, you got the Whirlpool Nebula, Globular Cluster. You got Markarian's chain, which Al kind of referenced when he was up here. With the labeling feature on the C Star, which was kind of cool. I didn't even know that existed. So figure that out. And there's also another feature called the framing, which I messed with to get a larger picture, a bigger area. And I used that with the Markarian chain. So we got the Pinwheel Galaxy to the right. So when we did have a clearing, it was pretty good. But from what Brandon was telling me, other times that y'all have been there have been much better. Clearer skies, less humidity, not as much haze, and these pictures probably would look a lot better under better conditions. So this is what we got. So what did we do? There are things to do over there. We had the caverns, $28, but well worth it. Probably the most impressive caverns I've ever seen. There was a wishing well in the middle. I wish for cleared skies. So don't waste your money. It doesn't work. To the north of Sonora, there's a place called the Hummer House where Alan went to with his wife. It's a bird sanctuary where they tag hummingbirds, I believe. Is that what they do?
Yeah.
And if you're not staying there, you could only go there on Saturday. You know, that's the only time it's open for outside, for people that actually physically aren't staying there. It's like a bunch of cabins and stuff, I guess, that you can stay there. So there are things to do. And so if you can't see the stars, you might as well go into the caves. Again, real impressive. I took tons of pictures, but that's all I'm going to put there. You got trails right there at the facility over at X Bar. It's called the Green Trail, but the green ribbons, which you can see on the left, are starting to look a little yellow. So sometimes you'll think you're on a yellow trail. It's on the app. It's on the what is the app? All Trails app. So you won't get lost. Really neat trail. Don't do it in the middle of the day when the sun's coming out. That's when we did it. So that wasn't a good idea. And that's it. Again, great facility. I would go back in a heartbeat. This is kind of the sponsors to the El Dorado Star Party. You could either stay where the cabins are or stay in the fields. If you take an RV, the fields is where the sewer dump is. So if you need to dump your tanks on your camper, that's where you need to go. And that's it. Any questions? Oh, I forgot. I donated, if you saw my telescope, a sticker that kind of looked like the logo of our club. I got a bunch of stickers made up for the club. So that's my donation.
Yeah, thank you for doing that.
All righty.
Okay, so next month, June 13th, right here. We don't know what we're doing. We'll figure it out. Door prizes. Anybody not get a door prize ticket? Where are the door prizes? Anybody not get one? Okay, good. By the way, this is the Tom and Cindy's last day here with us. So we've enjoyed having them as our members. They're moving to South Carolina. All right. Door prize. $464.